Yeah, thanks for coming. I want to talk about the latest work we did in Aarhus. So this is about MozZarella. And there we constructed Vector-OLE for the rings Z to the K, and we built zero-knowledge on top of that. So this is joint work with Alex, Carsten, and Peter, all from Aarhus. And yeah, let's go. That doesn't go. That go. So let's dissect the title. We are talking about Vector-OLE. So Vector-OLE is a functionality that can be seen as kind of a generalization of oblivious transfer, but now the receiver doesn't just have a bit, but it has a scalar in some larger ring or field. So here, like, we have a sender and a receiver, as they're usually called, and the sender has a vector x, which is usually the message, and the receiver has a scalar delta and another vector k. And this functionality takes these values and computes m as delta times x plus k. So we can also take a look at a random version of OLE, where all of these values are just sampled uniformly at random, so that this condition holds. And here R is so far just an arbitrary ring or field. But we will instantiate this later. So then zero-knowledge proofs. Of course, we have a prover, we have a verifier. The prover wants to convince the verifier that it knows some witness. And we need soundness. The prover should not be able to convince the verifier of something false. And zero-knowledge, the verifier should not learn anything. So we are considering zero-knowledge for circuits. So it's kind of circuit satisfiability. And we can consider Boolean circuits over like 0, 1 with XOR and AND. Or we can use arithmetic circuits with some larger ring or field. And we can also combine them in some kind of hybrid circuit. We are in the commit and prove paradigm. That means the prover commits to its input values, like its witness, all the intermediate values of the circuit and the output, and then in the second step proves that these commitments are consistent with what the circuit should compute. And our goal is to create zero-knowledge proofs for a designated verifier with linear communication on the circuit size and linear prover and verifier running time. And the idea is to get like an overhead that is as small as possible compared to the normal evaluation of the circuit, like if we would just evaluate this circuit in plain. And this would allow us to construct proofs that scale to very large statement. So the prover doesn't need much memory or much computation in addition to what it would normally use. The last part, Z to the K, we are interested in the integers modulo a power of 2. So normal addition multiplication, but mod 2 to the K. Why? First, it maps like naturally to data types that are used in modern programming languages or CPUs, where we have 32-bit or 64-bit integers. So it's exactly like the same set of numbers. And that makes it easier to convert computer programs to circuits. So if we want to prove statements about programs that we already have, that might be easier to get in the right form. And moreover, implementation of protocols can also be more efficient because we don't need the modular reduction modulo prime p, but we can just cut off all the bits that go beyond 2 to the k. On the downside, Z to the k is not a field. So we have zero divisors, we can't divide by any multiple of 2. Polynomials can have lots of roots, so this makes it harder to design a nice protocol. Because many of the tricks that we're used to from protocols over fields, they don't work anymore, or they don't work as nicely as before. So our protocols can get more complicated and the proofs get more messy. But I think the advantages are still a good reason to look at this setting. So today's talk is, it uses some stuff from our paper from last year, which my colleague Alex presented here, I think, virtually sometime last year. But the main part comes from MozZarella. Where we construct Vector-OLE and faster zero-knowledge proofs than before. So first, for commit and prove Vector-OLE, we of course need commitments. So I'm going to talk about how to construct linearly homomorphic commitments from Vector-OLE. then how to instantiate this Vector-OLE efficiently, because that is the new point that we could not do before. And finally, how to get to actual zero knowledge for circuits. Good. So let's take a look at commitments. If we are in a large field, we can just use information theoretic max to authenticate values. So here X is a value that the prover knows, and the verifier has some MAC keys, delta and K, and then the prover knows the corresponding MAC tag. And if the prover is able to open such a commitment to do different values by coming up with some different X and X prime and corresponding max M and M prime that satisfy this equation, we can show this is equivalent to guessing delta. And if delta is somewhat from a large enough domain, then this is unlikely to happen. So far, so good. Maybe notice that the MAC equation is exactly the same thing we get from Vector-OLE. So we can use Vector-OLE to efficiently generate such commitments. Now what happens if we're considering Z to the K? So as said before, it's not a field anymore. We can't divide by 2 or any multiple of 2. So if we would try to make the same proof of binding work, at some point we need to divide, and then, well, that's a problem, because what if like our 2 messages differ by like a multiple of 2? And well, the proof doesn't go through. Moreover, if we consider a value X that has a 1-bit error in the most significant bit, then the adversary only has to guess the least significant bit of delta to forge a MAC. So we only get soundness on half, because we don't have this field, we don't have the wraparound modulo prime, but all bits that are, well, above 2 to the K get cut off and dropped. So we are losing soundness in this case. And the solution is based on, well, the max that are used in the speeds 2 to the K MBC paper. And the idea is we take X, but we authenticate it over a larger ring, where like the size is now at least S bits larger than 2 to the K. So as a security parameter, and this allows us, if we consider like the K bits of X and multiply that with S bits of delta, then we don't lose anything of this product. So the idea is to authenticate only the lower K bits, but over the larger ring. So instead of using X directly, we need some representative of X in the larger ring that agrees with X on the lower K bits. Then we do anything, the other part as usual. So we sample delta from that 2 to the S, K from the whole ring, or there L should be equal to K plus S, compute the MAC tag, and so on. So we have kind of the same, but only the lower K bits are actually authenticated. Unfortunately, we are only interested in K bits, but we have to make do with a lot of more bits, or some more bits. So we have more storage, more communication, and arithmetic also gets more costly if we increase L beyond a certain size. So we have commitments. They are linear, so we can easily add them together, multiply them by constants, and that is locally. So if we have a prover committing to a bunch of commitments, then prover and verifier can compute a linear function on these commitments and get a new one without any communication. To open, the prover just publishes this representative X tilde, the MAC tag, and the verifier checks that this equation holds. But we have to be careful, because like the upper bits of this representative might depend on intermediate values in the computation before. Because if we look at computation modulo K, then every carry bit that goes beyond 2 to the K just disappears. For instance, we have this larger representative, they may still be there. So therefore, before opening, we need to blind them with a random commitment. Finally, we can also use a batched open procedure, for example, by sending like a hash of all the max instead of them separately. But we still need to blind the upper L minus K bits. So this is all from the old paper from last year, but we kind of need this in our new zero-knowledge system as well. Good. Now we have this equation, m equals delta times x tilde plus k. How do we get there? With Vector-OLE. So let's talk about that. Our functionality looks as follows. It's the same as before. Now the ring R has replaced by z2 to the L or z2 to the S for delta. So we can choose delta smaller according to the security parameter. And we want this equation to hold. We're still in the random setting, so we just want to generate a very large correlation of this form, so with large vectors. How could we do this? So one approach is to use oblivious transfer, but then we need one OT per bit of delta to multiply. So if delta is as large as the other ring elements, we get communication quadratic in the bit size and also linear in the vector size, because like every OT message needs to be as long as the whole vector. That is, I think, the instantiation they use in speeds 2k to compute these Vector-OLEs of z2 to k. On the other hand, there has been a recent line of work on pseudorandom correlation generators, which use a short interactive protocol to distribute a short seed among parties. And then the parties can expand this seed non-interactively into a long correlated random string without talking to each other. And the nice thing about these PCGs is that they have sublinear communication in the length of the correlation they obtain, which is very nice compared to the OT-based approach. These protocols rely on some variants of the learning parity with noise problem, about which I will talk in a minute. But unfortunately, if you want to avoid using like generic MPC for the setup, we only get active security for fields. For example, by Wang et al. Or Boyle et al. From the last years. But so far, nothing has been done for the ring case. And that's what we want to do. So we are getting actively secure Vector-OLE for z to the k with sublinear communication on the vector size. So that's our goal. And as promised, I want to recap the learning parity with noise assumption. So here we have a short, uniformly random secret or seed. And the assumption states that if we use the encoding matrix of a random linear code to encode this short random seed, and then add some sparse arrow vector on top, then this whole thing should be indistinguishable from a long uniformly random vector, given that this matrix is public. So here we use a variant that E is regular. That means E consists of several blocks, and each block has one non-zero coordinate. This assumption has been used for different fields, so F2 and also larger prime fields, and we consider it over Z to the K. We looked a bit at attacks, but we did not find anything that were like Z2 to the K would help an attacker to actually distinguish. So why is this assumption nice? Because it is linear, so it's compatible with this Vector-OLE relation that we already have. And that means we only need to generate like a short random Vector-OLE, and then we can expand it in a long pseudo-random looking Vector-OLE. Okay? So this is what our protocol actually does. We take a short number of Vector-OLEs, called seed or base Vector-OLEs, and we can use some expensive protocol, for example, based on oblivious transfer for this. And now we are extending this short correlation to a much, much longer one using LPN. And then we can repeat this to get like arbitrary many Vector-OLEs, basically. So we start with some Vector-OLE correlation that of like a random secret U, which is our base Vector-OLE. So here we don't care about where does this come from. We just assume there is a protocol that gives us this short correlation. Then we make use of a specialized subprotocol called single point Vector-OLE, where the message of the sender has a single non-zero coordinate. And we use this a couple of times on smaller vectors to get a long sparse Vector-OLE correlation. So where this E has T non-zero coordinates. This will be our error in the LPN assumption. If we have both of these, we can apply the encoding matrix, add everything together, and since this is compatible with the Vector-OLE relation, like everything is linear, sender and receiver can just both apply this locally to get a long Vector-OLE correlation z equals delta times x plus y that looks pseudorandom to them by the LPN assumption. So we can just use all of them, or we can just save m Vector-OLEs out of the many more we have, and then we can repeat the process over and over again. So this protocol, or this template, is based on Wolverine, which does Vector-OLE for fields, or for extension fields. This high-level setting is almost the same, and the interesting part is the single-point Vector-OLE, because we haven't talked about how this works yet. Everything else is basically local computation. So single-point Vector-OLE is what I want to talk next about, because the actual interesting part, and the part where we actually need to do some work to make it work with that 2 to the k instead of a field. So the goal is to generate this relation w equals delta times u plus v, where u has like a single non-zero coordinate at position alpha. If we look at this relation, we notice that w and v are both pseudorandom, or they both look random, and they are almost the same. There's just one coordinate, 1 point alpha, where they differ. So what do we usually do if we want to compress like a long random string? We use a PRG or PRF. So we almost do the same, but we use a punctured PRF, and punctured at this position alpha. So the receiver samples the PRF key, and then we can use oblivious transfers to transmit a punctured key to the sender. And this punctured key, k alpha, allows the sender to evaluate the PRF at all points but at alpha. And then we just set the vector v as like the full domain evaluation of this PRF. So since v equals w almost everywhere, the sender can compute the same. And what is missing is like the one coordinate w alpha. So how does this work? Well, we use the usual GDM construction, which is like the standard tool for this kind of punctured PRF. So we have a length doubling PRG, we expand the seed over and over again until we reach like enough output. And then what we want is, we want to remove one value from this domain. So normally S0 is like the secret key of the PRF, but we want to give the sender a key that allows him to learn like all leaves, but the one which we removed. So if we give them like these green nodes in the tree, then the sender can compute all the nodes below the green leaves. So all but V3. Since the tree has a logarithmic height, we only need to transfer logarithmic and not linear amount of data. And we can use oblivious transfers for every layer to actually get these green nodes to the sender. So that's the basic idea. Now we have almost the whole correlation, but we're missing like one part. So what do? We use another base Vector-OLE, and then the receiver sends a correction value. Okay, so this whole thing looks uniformly random because there's like one value in the sum, namely V alpha, that the sender doesn't know. So that kind of hides its correction value. And then the sender can compute the missing value of its correlation. So that's basically it. That would be the semi-honest protocol. But what could be wrong, especially if the receiver is corrupt? So it can cheat in two places. First, it can use inconsistent values to the OTs to transfer some garbage punctured key to the sender. And it can also induce an error in this correction value D that it sends. So in both cases, we get leakage on the coordinate alpha. Because the sender might abort if it gets garbage, depending on the OTs that they use. And since the sender uses the bits of alpha as choice bits in the OTs, we get a selected value tag there. And that is for the second problem, the receiver can put some errors, for example, in the upper bits of D, and can use this to tag some values, which might allow him later to learn where this the coordinate alpha actually was. So leakage on alpha is bad because in the LPN system, if the adversary knows alpha, then it can remove like the noisy coordinates from this linear system of equations and then just use Gaussian elimination. So we want to prevent that. What was done before? In Wolverine, they used a random linear combination. But that's a bit tricky in Z22K because, well, we are only interested in the lower k bits, but we would need to enlarge the ring by s bits again to have consistency in the lower k bits. But this means we can't just repeat this process over and over again. Like we can't just keep m out of the generated Vector-OLEs to start a next round, because in every round we would get smaller and smaller. So this is not satisfying. What we do instead, we have two separate checks. First, we check that this GM tree is consistent, which is kind of based on a check in a prior work by Boyle et al. So we have this tree again, and we expand it by one layer. And now we use like every second leaf on the last layer as our actual outputs. And the right siblings we use as checking values, and we ask the receiver to compute a universal hash function on these checking values t. And if we assume that the PRG that we use in the last layer is right half injective or right half collision resistant, then we prove that it's hard to come up with a hash that is consistent to multiple different values of alpha if the tree is not consistent. So the receiver sends us a hash in addition to all the other stuff, and then the sender can recompute it and check if it was consistent. So instead of using like cryptographic hash function, we showed that a universal one, which is faster to implement, is also sufficient. Good, we have solved the first issue. What about the second? Well, we use a linear combination after all, but we only use binary coefficients. So with binary coefficients, we don't have the problem that the product of our bit and the value is just moved out of the k bits. So we don't lose anything by the modular reduction. However, we still might get a problem. So the receiver doesn't know chi alpha. The receiver doesn't know alpha, but it can guess chi alpha. It's either 0 or 1, so the receiver guesses correctly with probability 1/2. We tried to prevent that, but at some point we thought, okay, let's be fine with it. We just leak the coordinate with probability 1/2. And then we compensate for this by increasing the noise value in the LPN problem overall. So if we assume statistical security, say 40 bits, then we want to make sure that the LPN problem is still hard if we leak 40 coordinates. because like every time in every single point Vector-OLE, we have probability 1/2 of failure that the corrupted receiver guesses wrong, and then the sender would abort. So yeah, that's the idea behind the single point Vector-OLE protocol. Well, we accept the leakage, but we increase the noise overall to make this work. Good. Now we have Vector-OLE. We have linear homomorphic commitments from Vector-OLE. How do we get zero knowledge? So we have these commitments. And these commitments are linear, as we have seen before. So we already have linear, we have zero knowledge for linear functions. The prover can commit, both parties compute the linear function, the prover opens the result. But now we want zero knowledge for arbitrary circuits. So what is missing is multiplications. How does the prover that it does multiplications correctly? So it commits to the output of every multiplication gate in the circuit, and then it proves that for such a triple of committed values A, B, C, C is indeed the product of A and B. So that's the missing part. In A to B, we gave already two variants which use like black box access to the commitment scheme. The first one was based on the zero knowledge part of the Wolverine paper, which uses a bucketing approach with untrusted beaver triples to do multiplication. And the second part was an adaptation of the mac and cheese check, which is in turn based on speed style sacrificing. On the other hand, so the second check is nicer because it doesn't need the bucketing, but it needs a larger message space. So there's kind of a trade-off, because we need now to authenticate elements of zk, z2 to the k plus s over the larger ring z2 to the k plus 2s. But yeah, so that's prior work now. And in this work, we are introducing Quacksilver, which is an adaptation of the Quicksilver protocol. So the authors of Quicksilver looked at the MAC equations. So, well, here I kind of swapped the position of k and m, but you can just flip the sign and then this is already fine. But this presentation is nicer for the use here. So if we multiply the MAC equations of A and B and then like subtract delta times the MAC equation of C, then we get a polynomial in delta. So we have one part over here, like the first part. This is known by the verifier. The verifier knows all the k's and it also knows delta. On the right-hand side, we have two coefficients A0 and A1 that the prover knows. So it knows all the MAC tags and all the plain values. And the coefficient of delta squared should be 0 if the prover is honest. So if A times B is indeed C, then this is 0. So we have a like degree 1 polynomial. And now to check, the prover can send the coefficients A0 and A1, and the verifier checks that this actually fulfills this equation. So why is this sound? Oh yeah, we can also apply random linear combinations on top of that to aggregate, and then just have one check for many commitments. So why is this sound? So say we have an error in our multiplication. So A times B minus C is non-zero. And then the prover sends some values, A0 star and A1 star, which also might have some additional error term. So we can see the verifier accept as the equation above holds true. And if we subtract the big equation, then we get something like, oh, where's my cursor? 0 equals E1 plus E0 plus E1 times delta plus E times delta squared. And since we say, oh, the prover is cheating, we know E is non-zero. So we have a degree 2 polynomial here. So to convince the verifier that the prover did everything all right, so to successfully cheat, the prover has to guess a polynomial with coefficients e0, e1, and e, so that delta is the root of this polynomial. But delta is chosen uniformly at random. And since over a field, every degree 2 polynomial has at most 2 roots. So it's really unlikely to come up with these values e0, e1, and e, so that this check goes through. So that is great. On the other hand, well, we have a ring. So we can have lots of roots. And we actually took quite some time to bound the number of roots that this polynomial has if we do all of this modulo 2 to the k. And then we end up with something like 2 to the s half roots. So like a square root of all possible values are actually roots of such a polynomial at most. So it's an upper bound. So the soundness is probably not as nice as before. And to compensate, we enlarge the modulus again. So now we are computing modulo 2 to the k plus 2s plus 2 log s plus 3 or so to get s bits of statistical security. So that means if we target like 40 bits of security and we want to have 64-bit values, then we have to use approximately 160 bits of a ring. And I think with 80 bits of security, that goes to 240 bits approximately. I'm sorry? So delta must be the root, and so k is the message space that we're interested in. So could be 2 to the 8. Okay, could be 8. But delta is larger. Delta has size of security parameter, approximately. So yeah, delta lies in this range. Now we also have a kind of a trade-off, because if we make delta, or if we sample delta from a larger space, then this polynomial has more roots. But if we take a smaller delta, then it's easier to guess. So yeah, we need to find something in between. And yeah, so this is basically what I wanted to say about the zero-knowledge protocol. Our contribution is basically hidden in how many roots does this polynomial have and making all of the stuff work. So we have seen how to do Vector-OLE, how to get linearly homomorphic commitments, how to do zero-knowledge on top. Is this actually efficient? Well, we implemented some benchmarks. We used this swanky MPC framework from Galore and yeah, wrote this in Rust. So if we take a short look at the Vector-OLE numbers, below we have like the numbers from Wolverine, and yeah, everything is nanoseconds per Vector-OLE. So nanoseconds per entry in this long vector. And well, we can see that the numbers in Wolverine are not too different from the numbers that we get here in the upper part of the table. The highlighted row would be the size of the ring that we need for 64-bit Quarksilver. So it is a bit larger, but also not too much. But yeah, mainly we need more communication. And I also get to that in a second. And we can also see that our protocol is at some point computationally bounded, because if we just increase the bandwidth, then it won't get much faster. Let's take a look at the zero-knowledge numbers. So, okay, so in this table we split the running time and like into network settings into the different parts. So the Vector-OLE, the actual multiplication, and the check in the end. And well, maybe, so it was somewhat surprising that the multiplication check was actually the bottleneck. Or not the check, but the multiplication was actually the bottleneck. But it was also the part of the protocol where we have the most communication. So here we can see we have one ring element of communication. So this is rounded up to the next multiple of 64 bits due to our implementation. Overall, we get about 1 million multiplications that we can check per second. The original Quicksilver for fields got a bit higher, so they achieved, I think, 5 million multiplications in their implementation. So, but does it mean like they are much, much better? I wouldn't say so. So why are we slower? We need larger rings. So we need like rings of the size. So they are, if we implement them in like blocks of 64 bits, they are 3 or 4 times as large as the field that Quicksilver uses. So of course we have much more, or we have more expensive arithmetic. I think a computer like wants factor 6 more 64-bit multiplications or so. And we also have to transfer much more data. So that kind of makes up for the difference. On the upside, we have native 64-bit arithmetic. So we can take two 64-bit values, two arbitrary values, multiply them, and we get the correct result modulo 2 to the 64. Quicksilver uses Mersenne prime field. I think, yeah, about 2 to the 61 minus 1 or so. And that means they can't even represent 64-bit values. And even if they multiply two arbitrary 32-bit values, they get problems with like the modular wraparound. So we can say, yes, we are more expensive, but we also have more features. So to summarize, we give like the first actively secure Vector-OLE protocol for the Z2 to the K setting with sublinear communication and like the correlation size. And yeah, for this we have like a bit more of communication per vector entry. So if we have a really large batch, such as like 10 to the 8 vector length, then we get down to this. So it is very, very little. We showed Quarksilver, which is the adoption of the Quicksilver protocol in the G's world. And there we get zero-knowledge, where we have to transfer one ring element per multiplication check. And that is the ring element we need to send to actually commit to the output of the multiplication. So the question is, how can we make this more efficient? Because we need to work in this larger ring. How can we reduce this overhead compared to the k-bits that we are actually interested in? Because everything in addition to the k-bits is overhead that we don't want, but we don't need. So the question is, how far can we go down? And then many protocols that appeared recently uses like polynomially based checks, similar to the Quicksilver check, but also for higher degrees. And then things get messy, because if we just generalize the current approach, the number of roots of polynomials over Z to K just explodes. So we need to increase the ring size more and more, and then that is not really efficient anymore. So I would really like to know if we can get some alternative to these polynomial-based checks that also works in the ring settings. Okay, that's what I wanted to say today. Well, thanks for listening. Yeah.